Alright, higher degrees, higher powers. So higher degree polynomials or higher powers. Alright, so if we have, look at some patterns.
Yeah.
Factors of the form. So if you have, say, x minus a, we can get intercepts from that, and then what that will tell us is that it cuts the axis. Alright, so if you use our a, so whatever the polynomial might be, it cuts the axis there at a. If you then have a repeated factor, then what happens there at the axis? Turns around. So we have a turning point on the x-axis for that one. So that would be something like this. Then if we have, say, a factor x minus c that's cubed, what's going to happen then? It's going to cut through, yes, it will cut through, but something else is going to happen there as well. It's going to go like that, so yes, it's going to have a
Inflection.
point of inflection, POI. Alright, so it's going to go like that through the axis. And then of course for higher degrees you can have combinations of those things as well. Hot. I need to do across the bottom bit too. There you go, there's that. Alright. So we'll start off with a sign diagram and then we'll do an example of sketching and then you're away. Alright, example. Jared. Alright, when we were doing this the other day, some people struggled a little bit with this factor. So, if you want to look at that, I could rewrite just that factor. I could take -1 out as a factor and then write it as x minus 2. That's another way I could write that. So if I do write that like that, then this particular, this -1 at the front tells us what? It's reflected. Right, so it's a reflection. In the x-axis. What sort of power would it be? Would be power of 4. So it's a quartic. Now normally all even powers would start where?
Top left.
Would start top left. All even powers start up here and finish up there. But this one's reflected. So this one therefore will start under axis. So start bottom left. Alright, so when we're drawing and our x-intercepts, where would our x-intercepts be? They would be at 2, -2, and 5. So when we're drawing our sign diagram, we need those numbers. And there they are. Positive up here, negative down there. So remembering positive means it's above the x-axis, negative means it's below. And we are starting bottom left. So if we're starting bottom left, we're starting down here. And then there's no repeated factors, so each time it gets the x-intercept, we'll do that. So there's our sign diagram.
How would you draw that as a normal?
How would I draw that as a graph? Yep. So if we wanted to draw that as a graph, so we'll have x-intercepts at -2, 2, 3 and 5. And we know, so if we put f of 0, we get 2 minus 0, 0 plus 2, 0 minus 3, 0 minus 5.
-2 plus 2, which is
2
0.
times 2 times -3 times -5. 2 2's are 4, 4 3's are 12, 3's are 60. No, 36. 12. 2 2's are 4, 3 4's are 12, 5 12's are 60. So this is going up here somewhere. Perhaps I won't Perhaps I won't draw it. And then it's coming down here and going.
It's a bit rude.
Does that answer your question there, Carla?
If that was in a test, would we have to draw it on the page?
Well, in the test, the graph would suit.
Yeah, they will give you a thing that would.
But can't you just make it 60? Be like, oh, 60 is like there. And it's
On exams, when they've got you to draw things, they've given you
enough space.
Yeah, they've given you the graph paper, so to speak. So you need to do it. But yeah, otherwise you could just go.
So how is that a quartet?
Because it's 4. Ah, good point.
How's it a quartic?
Because I don't-
Wouldn't the,
I
wouldn't
thought that
the,
just meant that it was flatter on the bottom.
does that mean?
Well, that's if it's a perfect quartic. Because like cubes, if you have a perfect cube, then yes, it goes like that. But if you have a cubic that's
Not perfect.
Oh,
not a
'cause this is,
perfect
this
cube.
is sine graphs.
then it,
Yeah, but it still can be graphed as a normal graph.
Ah, as
That
in like
doesn't-
SIN.
But that one doesn't look, that still looks like a x cubed graph. That one does not look like an x.
oh, it's got an extra wiggle, hasn't it? It goes wiggle 1, 2, 3. This has got 1, 2, 3, 4 wiggles.
How many wiggles are there supposed to be?
There's 4 wiggles, isn't there?
I don't know.
So this is the blue wiggle. 1 wiggle up, 2 wiggle,
Yellow,
3 wiggle,
purple,
4 wiggle.
red.
Oh,
Isn't purple?
So 1, 2, 3.
There's
Yeah.
3 wiggles.
1, 2, 3, 4.
Yes.
And a pair of 5 goes up again, and a pair of 6 and 7.
9, 10, 11.
And then keep going.
I can't get my head around that that is
I know.
the same basic form, like the basic form of that is like an x squared graph, but flatter. Like,
Well, it's not like an x squared graph. It's only when it's a perfect, like this perfect power of 4.
Oh, I
Then it's
just got it.
like that instead of like.
Now it's,
yeah.
I just got it.
Because, no,
Right.
if you think about it, each point, 2, x plus 3, x plus 2, they're all linear. They're all linear.
they're all linear.
But if you add them all together, they're like, it creates different linears. Think of it like that.
Yeah, so here it starts here and it cuts through there, as you say, a linear factor cuts through, but then it's got to get back to here, so it's got to turn around and
So
come
it's
back,
not
doesn't
another
it?
linear.
And then it's got to get back to there, so it's got to turn around and come back, and then it's got to get back to there, so it's got to turn around and come back.
Okay.
If you had one of those powers, and if it was like 8 powers, and one of them was a power of 4, would it then be a
It'd
like
be
very more squared?
1, 2, 3, 4.
Yeah, it would be
So, for example, let's go.
There you go.
Does that mean
I think
So
at
let's
the
make
top
some-
near the 60 bit it's going to be really flat? Is it going to be flat near the 60 or not?
The mountain.
If
Oh,
it's
it probably will be, yeah.
Okay. It's flatter than it would be if it was a
Probably, yeah.
x squared.
So if we've got, so x minus, so we've got that, and this one's got a power of 4 on it.
Yeah.
But it's like a repeating factor.
It is like a
should be a
repeating
turning
factor.
point.
Correct.
Yeah, what is it happens at a power of 4?
So this is power of
Numero uno.
1. So and a power of 4 there. So altogether, what's the power? Power of.
5.
37.
So it's an odd power of x's.
Which means it looks like
Starts up here. So it starts up here.
Why is it
The
not?
linear factor, Byron, cuts through. Yes.
Yep.
Yes.
But then it's got to come back to there. Now, when it comes back to there, what's that? That's power of 4. So that's going to be.
Well,
It's
like a flat turning
wow.
point.
What the?
That's going to
It's
be
like a
flat.
plateau.
Surely they're not going to be.
What happens, I know I'm going off topic, but what happens like to the power of 2 and then to the power of 4? So if you replace
It'd
that
be
power
It
of
would go
1,
up and then it would
be
come down.
Turning point.
because the power of 2 is like, it's repeated factor.
There's also just this.
Actually, I've started that the wrong place, haven't I? That one?
Yep.
I should have started it down here, shouldn't I?
Yeah.
Because negative powers start down here, don't they?
Ooh.
Negative power.
Wait, what's negative about it?
Sorry, not negative, odd powers.
Ah,
But that's it's
I
6.
thought I was going.
Now, the red one's
There's
power of
6.
6.
Ah.
So this is power of 6.
Yep.
So even powers start up here.
Yep.
turning
around
point
on
there,
one,
normal turning point,
comes down again,
comes down again,
and is flat.
flat turning point.
Oh, okay.
Alright.
And then if it's reflected, then it goes the opposite way.
Oh my god.
That's
So,
actually so much fun.
if you had like a 5 or a 7 or something, it would just be flatter. Like it just progressively gets flatter.
Progressively gets flatter, correct.
Would we?
And that
That's
applies
fine,
to
second
2 and 4.
So people like get older.
That
than
applies to
the
like
power of
even
200.
numbers. That
Applies
applies,
to
Be
odd
like a
numbers
straight
too.
line.
yeah, it applies to even numbers as well. Like it gets
Like
flatter.
that.
Yeah,
Yeah,
yeah.
as it
The
gets
bigger
flatter.
that power gets, that, whether it's a turning point or whether it's a point of inflection, the flatter and more square that bit becomes.
Okay.
Money time.
Cool, cool.
Happy with that?
I'm happy with that.
Can I answer your question?
We just went off content.
That was a rabbit hole. Just a You're right. Jared?
I mean, and this
Green.
kind of being able to recognise this stuff, like multiple choice question, which one of the following graphs or which equation could fit the graph kind of thing.
Okay, so we do need to know.
Hmm.
But we can just shove it in the calculator, right?
Sometimes they don't give you numbers, sometimes they give you A's and B's
It
and
might not give
things.
you much if you shove it in there.
So you might not be able
So
to
just get
shove it
rid
in.
of
Alright, let's sketch a graph.
Is this a long one?
No, not particularly.
Yeah.
Right, at the moment we're not going to work out what. We'll worry about turning points later. So when we get to calculus, there's easier ways of working out turning points. So we may or may not be able to find them easily here. Alright, so if we're sketching a graph, what do we need?
We need the intercepts.
Intercepts, right. So let's go y-intercept first of all, that's the easiest one.
Bada bing, bada bing.
X equals 0, f of 0 is
One.
equals 1. Alright, x-intercepts, what do we need to do?
Y equals 0.
Y equals 0, so we've got 0 equals x to the 4 minus 2x squared plus 1. Alright, now there is a technique that we can use here to help us.
Synthetic.
No, not going to use synthetic,
What did you say? Ew.
because we've got 3 terms there, so it kind of looks a little bit like a
We can't factorize the constant.
quadratic trinomial.
Yeah.
But it's a power of 4. So if I let a equal x squared, for example,
Where's that?
just made this up, I'm letting a equal x squared to make it easier to factorise. So if I did, I'd end up with 0 equaling a to the what? To the 2. So we get x squared minus 2a plus 1. So that does look like now a quadratic. 2 numbers that multiply to give us 1 and add to give us negative 2. Well, it can only be 1 times 1 or negative 1 and negative 1.
Negative 1, negative 1.
Negative 1, negative 1. So we've got a minus 1 squared, haven't we? Yes? No? Maybe?
Yes.
Sure.
All right. Now, if I put my x squared back in, what is now inside this bracket?
It's a
X.
dots.
It is a dot. So I can now rewrite that like this, and I'm just using the blue just to...
Yeah.
So I'm just using the blue bracket to emphasise, not because it needs to be blue. So those blue brackets are the same brackets, yeah?
Okie dokie.
And so inside that, that's adopts x plus 1 times x minus 1, yes?
Sure.
Why do you say it like that, Ben? Now, each of these brackets is what powers on each of those brackets?
Wait.
One at the moment,
Okay.
but
Yeah,
as
yeah.
Kayla said, index law says when we remove this blue bracket, we'll have x plus 1 squared and x minus 1 squared. What do we have then? We have some repeated factors, but in terms of x plus 1 could equal 0, or x take 1 could equal 0,
X equals -1.
negative 1, or 1. So let's have a look.
Turn around, -1. Yeah.
So we've got intercepts. Y-intercept there, x-intercepts there and there, and Kayla, at those x-intercepts,
Turns around.
turns around because they're repeated factors, yep.
Oh my god.
So repeated factors. All right, so it's a power of 4. Power of 4 start up here, and that's a repeated factor there. What do you think's going to go on there, here, in this, for this particular one? Anything special?
Ooh,
It's gonna
good question.
Question.
Why?
Because it has to go down to the 1 again.
Oh,
It
yeah.
has to go down to there again, and this is what? The middle
Yep.
of there?
Oh, so it's the
Turning
turning
point.
So it's probably going to be a turning point, isn't it?
There are a lot of turning
Oh,
points.
37.
Three
There
of
you go. W, big W. Yeah, chat.
If these weren't, if that wasn't the middle of those, then probably wouldn't be, but because it's the middle,
Be some sort of fraction.
yeah. So if that was 1 and that was 2, then the turning point
would be
wouldn't be right there, it'd be somewhere. But because that y-axis is the axis of symmetry, if you like, between that, it's probably a turning
So would
point.
you have to show the turning point if the turning point was not the Y?
Quite possibly, but then you'd use calculus to do that.
Would you add them up and divide them by 2? Like add the intercepts and divide them by 2?
Oh, it may not necessarily be that, but you'd use calculus to do it,
When you
which
do
we
that,
haven't done yet.
when you do that arrow for the repeated factor, was that to that whole thing, yeah?
Well, actually, it shouldn't go to there, really, should it? It should go to
To
that,
the-
should go to those. shouldn't it?
Okay.
They're the repeated factors, aren't they? I've been a bit lazy there. And because they're repeated factors, we know that the turning point's there on the axis.
Ruby.
All right. Well, that's it for today.
Yay, guys. What fun.
Very epic.
Wait, what?
Unless there's anything else, anything else?
This is 4F.
What the?
No. 4F it is, yes.
Ew.
Yeah. Okay. Michael's gonna be broken. No, it's no, just